So I'm going to be discussing the exponential function 2 to the x, and with a focus on our log functions. So what's going on here? Well, these functions are actually inverse functions of one another. If we can see the reflection between y equals x, we can see the behavior of both of these two functions. That's what we're going to prove today. So you've got 2 to the x, and you've got log base 2 to the x. So the program only allowed me to do this, so that is log to the base 2. Now, what's going on? So our 2 to the x, no matter how small x is, if we look at our first function 2 to the x here, that if I put negative 3, 2 to the negative 3 power gives me 1/8. If we went back, say x is equal to negative 100, well then it would be 2 to the negative 100 power, right? And then we'd have some very gigantic number in the denominator, rendering that almost to 0. Of course, the graphs aren't going to go to negative 100 here, but you can see that even at small numbers, that this is getting really small. If this is 1, then as you go out further, you can see that y is becoming 0 along 2 to the x. But it never crosses. Well, that's exactly why our inverse function over here, which is the reciprocal of this across the line y equals x, is definitely going to not cross the y-axis. But why does this happen? Let's take a look at our table. I color-coded these so as you could see that the x values, right, become the y values for the log function. Let's look and plot a few numbers. So maybe we start at have to use our exponent rules, and we're going to get 1 over 2. Right, so that's the idea. Now, to be consistent with the... All right, so using this property, which we have covered before in previous videos, we can see that 2 to the 0, right, x can be 0. And that actually gives you the y-intercept for the exponential function 2 to the x. It's going to give me 1. So let's take a step back. Let's see what's going on with the log function in the table first. Here's the deal. When you're negative 1, you get 1/2 for y, but when you put 1/2 in for the log function, you get negative 1, or I should say 1/2 for x, which is why I'm color coding this, that you're going to get negative 1 for y. I want you to notice how the y value, now which is the dependent variable, becomes the independent variable for the logarithmic function. This tells us that in this case, right, that this is the whole y equals x property. I won't get into the minutia of this. This does take like a very mild justification for midpoint. So we'll just kind of trust our tables and our graphs and the things I discuss here that'll help to elucidate or reveal what's going on here with these two functions, which are inverses of one another. So negative 1 again gives me 1/2. That's the dependent variable y, dependent on x, now becomes the independent variable 1/2 x that gives us the dependent value, negative 1 for y in the log function. Guys, that's because 2 to the y by definition of logs is equal to x. We can see this graphically, and what I did to prove, and we'll go ahead and we'll do a few more values here before I get into the proof, but if you do x to the 0 power, again, you get 1 for y. That is the y-intercept right here for our logarithmic function. And then if you plug 1 in for x here, that means that 2, right, to the first power actually, what I meant to say was, this is why these things can be kind of tricky on the eyes, is that, 2, right, our log base 2, to the 0 power in y gives me 1 for x, right? So what's going on here is if I wanted to change these, I could do the inverse property. But let's look at the graph now, and I'll do a little bit of work regarding finding the inverse function here. I don't want to overwhelm you with doing that here, so I'm using graphs in lieu of that for now. So let's just look at our functions. How do we do this? Well, if you bear with me here, if you'll trust me to do this, what I'll do is I'll graph it where the x-axis is the vertical dependent and the y-axis, so that we can see what's going on with our logs. We still have the fact that y equals log base 2 of x. We're just seeing this as if it was the exponential function, right, where you've got 2 to the y. So in other words, I graphed this as its log function, but I switched the y into becoming the independent variable and the x being the dependent variable so we could see it in the graph as such. Let me explain. If we do 2 to the 0 power for y. So if y becomes 0, then we get 1 here on the x-axis, right? Let's look at our graph. So in the graph, I've got log base 2 of x. Let's see what's going on now. That's going to be the yellow line. That's the same thing. The only thing is that I've rotated and flipped it into the page. So you've got y and x here now, but it's still the same graph, just rotated. In other words, you're seeing these, and bear with me, it's not a complete rotation here, but as if it was rotated graph. So being able to visualize your graph and your independent and dependent variable from kind of looking left to right instead of up and down or down and up respectively, you're going to be able to see what's going on. Let's look at it. Let's prove that that yellow line with this rotated axis, respectively, is the same thing going on over here, just kind of as a visual flipped into the page. It really is on the eyes here. They are inverse functions, but let's go ahead and I'll explain what's going on here with this yellow line. Now, earlier I said that on the x-axis, if y is 0, that's going to give me 1. Well, let's look. That's true, isn't it? So what's really going on here is we're seeing our inverse function like this. That's what's going on in this case, guys. So in other words, when I see log problems, I don't see like this nonsense. I'm seeing it like this, and I'm also sometimes even looking at the graph. It really kind of helps to show what's going on. Now, I did promise I would do the inverse function. So let's go back a little bit and let's understand what's going on, or actually why we're on the topic of switching our log form here. In fact, I might, let's see, I might actually take this and go back to the original. So if we do our log property and we switch our variables, that's the whole thing behind inverse functions. Now, technically, if you've done this, you're already halfway there in finding the inverse function. The only thing left is for you to switch the variables. So you get y is equal to 2 to the x. We just simply switch them at the end. And we can see that that's going to be that blue function that we started out with way over here where I have this y equal to 2 to the x. So that is that line there. Let's take a few steps back. So in this, again, if I look at my orange function, I know that when I put 0 in for y, I'm going to get 1 for x. So I'm really kind of seeing this as the orange line. I'm just looking at it over here when I see this so that I can make better sense of what's going on in terms of x. It's what allows us to see it. And the cool thing about this, when you're doing the inverse functions, to find the inverse, and these are inverse functions in fact, is that as you work with the log function, you'll actually roll into the exponential function that I have over there in the table. So I'm going to go ahead and that is 2 to the x, and I'll read this out to show that that's what we had started with. Something like this, right? And we get that blue here. Now, so what's going on? Let's kind of go through the rest of this. 2 to the first power is 2, right? Then if I look at my other function for log, 2 base 2 of x, then now we can kind of see this through the numbers. We know that 2 to the first power is 2, right? So in other words, if I put x is equal to 2, I know that 2 to the first power, in other words, y is 1. Let's do this one more time. So if I put 4 in for x, I know that 2 to the second power, the power being y, which is your dependent variable, is equal to, again, 2 to the, if x is equal to 4, then 2 to the second power. So you're kind of reading it like to the dependent variable. I know it's a bit odd, but that's how these things go. Let's do it again. If we do it at 3, if y is equal to 3, I know that 2 to the third is equal to 8. So if you have x is equal to 8, then you know that 2 to the third power gives you 8. It takes a little bit of foresight when you're doing these. There we go. That means you've got 2 to the y is equal to, say, x. If we're looking at our log function, that's how I'm reading this. 2 to the y is equal to x. So then I have this. Let's go ahead and plug in what we know. We know 2 to the y is equal to 8, right? We don't know what y is. How do we solve this? Again, you can guess your numbers, or like before, when we were dealing with exponential functions, you can rewrite 8 and get to that answer. Let's do that. If we do 3, right now that we're at the same base, we can drop the 2 and y is equal to 3. In other videos, we'll be discussing how to do that without dropping the 2, why this works. For example, if you do the natural log, and I know it's kind of funky, but if you, or any log, it doesn't matter what the base is, then by using this log property, you can drop your y, respectively, and you get this 3 log 2. And notice how log 2 is the same. That divides out, guys. If you divide log 2 on both sides, earlier in prior chapters, we could see that that's what was, we didn't do this, but that's why we were able to set them equal to each other. We could just look at the exponents and solve what was left. Hope this helps. A little review on dealing with how we find that value without having to kind of guess through it. I know I kind of like, probably was shocking at first. You're like, why do I have to foreshadow? But this is what you would do if you really wanted to get to the prove why it worked. However, I wouldn't always recommend solving through it like that. The best thing to do would literally use my logic before. Just kind of follow that pattern. If you have 8, you know 2 to the something gets you there. If the numbers get so ridiculous that you need to use another log property, then we'll go ahead and do it like I did this one. If it's not so convenient, or you might not even be able to get the same base. We'll discuss other log techniques later on how we approach these functions when we get to more complicated numbers like irrational numbers or repeating numbers or numbers that just aren't nice.